In our YT coil for impedance matching video, we know mitigating the discontinuity through the impedance matching and SerDes interface is a must to improve the signal integrity SI. Therefore, we might need terminating resistors for low frequency matching and coils for high frequency matching, respectively. In this video, I'm going to focus on the terminating resistors, not the coils, and show you why you may need on-die termination, ODT, and its corresponding calibrations for the trimming accuracy in a SerDes. To clarify a few terminologies first, people may put the resistors for low frequency matching either outside or inside the silicon chips respectively. Outside the chip, people may call it external or off-chip termination. Inside the chip, people may call it on-die or on-chip termination. And we use the ODT to refer to the on-die termination for our following video. So, which one would be better? To reduce the reflection, we may consider which one would provide a more accurate resistance, such that the impedance matching would be better. Perhaps you could think about the size and accuracy of the image for 5 seconds. Right, the dimensional of the external resistors is much bigger than on-die resistor. Therefore, the ODT would have lots of variability in the dimensional from doping, lithography, stress, and so forth material fluctuation in a CMOS verification process. On the other hand, the external resistor may provide much more accurate and temperature-insensitive resistance than the ODT. Does that mean the external termination would be your choice in a SerDes interface? Think about the reflection one more time. Bingo! The reflection image already tells you the answer. One image is more than 1,000 words. But why do we see a big reflection difference just by putting the resistors in a different location? Alright, on the left hand side of the external termination image, after or behind the resistor, the unterminated stub came from the packaged LC plastic and the on-die circuitry at the RX front end. Then, the stub caused a big reflection in the signal patterns. That's the reason the reflection will travel back to the TX and in turn reflect the RX, causing a big defective voltage ripple or small I high. On the other hand side, the ODT image, the resistor is after or behind the packaged LC plastic as part of our RX front end circuitry. The terminating resistor eliminates the reflection with a slight reflection back to the TX and in turn reflected forward to the RX with almost not a reflective ripple. That's the reason you will see almost no ripple or a bigger eye in the ODT image. Again, there's a subtle images here. Any guess? Right, we assume both terminations are accurate in both images, but in some low speed links, the tolerance from the resistance accuracy is not that strict in terms of the signal integrity SI. For reflection, do you have any idea why do we need a precise ODT? Think about the multiparticle images for 5 seconds. Correct. Different media interface MDI may specify different requirements for the termination value. For example, the multiparticle MP SerDes should provide the differential termination to be 100 ohms for most PCB Trends in a backplane, a 150 ohm for a cable in a fabric channel, a 200 ohm for high swing and low power C-link, and customize like an 80 ohm or below value for very high speed bandwidth C-link. In addition, a default termination value not used during operation should be at least 20 kilo ohm or higher for hot plug support. After knowing why we may need a wide range and precise ODT, how do we implement the required resistance? Think about the voltage control resistance VCR image for 5 seconds. Correct. A simple MOSFET transistor operating in a trial region would behave as a voltage control resistor, and the resistance is controlled by the gate source voltage VGS. If the VGS is greater than the threshold voltage VTH, then the required 80 ohm up to 200 ohm can be tuned easily if the applied VGS is precise. Also, if the VGS is less than the threshold voltage VTH, then the device is off as an open switch and has high resistance, which should be greater than 20 kilo ohm easily. If we assume we could generate a precise VGS to achieve a precise 80 ohm, 100 ohm, or 200 ohm respectively, does that mean using the simple MOSFET transistor as a VCR is the best choice? If not, why not? Think about the signal integrity, speed, and reliability image for 5 seconds. Right. The first robust performance image is linearity, which depends on the VDS. If the swing across the transistor is huge, which is usually the case, the bigger VDS across it would degrade the linearity and make the signal integrity nasty. The second speed image is the passive capacitance from the device, which also could be measured by the voltage across it, that would degrade the signal bandwidth to limit the maximum operating speed and good signal integrity. The third reliability image is the electrostatic discharge (ESD) reliability limitation of the active device. Due to so many poor images of the MOSFET, you probably would like to seek another device to turn those poor images into good images. Any thoughts? Think about the passive images for 5 seconds. Bingo! The first good image of the on-die passive resistor is a good linearity, which can tolerate all swing across it. The second good image is a less passive capacitance, even non-zero, and that would not degrade the signal speed too much. The third better image is the more tolerance for the ESD, even though an ESD device is still a must before being attached to the I/O interface. But this single resistor is not tunable. How do you make it? Think about the switch images for 5 seconds. Correct. Why don't we add a transistor as a switch, not a VCR, to make the selectable resistor legs? For example, first, more resistors legs are selected with all transistors turned on, and the overall resistance could be minimal to 80 ohm. Second, fewer resistor legs are selected with more transistors turned off, and the overall resistance could be increased to 100 ohm or even 200 ohms. Lastly, as all resistor legs are disabled, with all transistors being turned off, the overall resistance could be a high impedance or more than 20 kilo ohms. Now, you may wonder, how do we choose the digital code to select the switch, which is why you need on-die termination ODT calibration for the trimming accuracy in a SerDes. After knowing why, could you please think about the negative feedback images for 5 seconds. Yes, the most reliable one would have a background calibration loop with a negative feedback continuous loop for the undiagnosed termination change. Of course, the external resistor owing to the most precise should be a reference, then a precise current flowing through it would generate a reference voltage as the comparison reference. The sense undiagnosed termination ODT would have the same precision current flowing through to generate the sense voltage as the monitor voltage. If the sense voltage is less than the reference one initially, the converter output would make the counter in a state machine go up to increase the resistance by turning off more resistor lag and vice versa. Let me give another direction image for your exercise. I assume you may agree this negative feedback background calibration would provide the most precise resistance value as the external resistance. Is that the best approach? If you suspect it, could you please think about the noise images for 5 seconds? Very good. If the calibration does not stop, the digital code of the switch likely dithering between 2 or even 3 adjacent states. Therefore, the resistance of the ODT will keep varying over time, which produces the dithering voltage noise at the input-output front end and degrades the signal integrity. So, what can we do? Think about the static trimming images for 5 seconds. Correct. As we have shown in the YT coil video, the accuracy requirement is not very strict. As long as we can calibrate to the target 80 ohm, 100 ohm, or 200 ohm ballpark range, the resistance variation over temperature and voltage around the range should be still acceptable and good enough. Therefore, we could do the negative feedback continuous loop for the ODT change while we power on the chip, skipping the dithering and just picking one cross or most likely hook core as a fixed core in the normal continuous operation. Therefore, the resistance value would not have any background dithering noise, but slightly less precise resistance over temperature and voltage variation, which is okay. In our experience, this foreground digital calibration for the trimming accuracy in a SerDes is the image people prefer. Here are the summarized images of why you may need undiagnosed termination ODT and its corresponding calibration for the trimming accuracy in a SerDes. To reduce the signal reflection, we may need to provide an accuracy resistance with the best impedance matching. Even though the external resistor may provide a much more accurate and temperature-insensitive resistance than the ODT, the external termination with the packaged LC passive and the undiagnosed circuitry at the RX front end creates the unterminated stops and a big reflection in the signal path. On the other hand, the multiparticle and SerDes will provide a differential termination range widely to be 100 ohm for most PCB traces in a backplane, a 150 ohm for a cable in a feedback channel, 200 ohm for high swing, low power C-link, and customized than 80 ohm or below value for a very high speed C-link, and greater than 20 kilo ohm for hot plug support. Therefore, a tunable resistance is a must. Even though a MOSFET transistor is easy to tune however you want. The poor image of linearity over swing, passive capacitance, and ESD may push us to choose a slightly complicated passive on-die polysilicon resistors with a few switch legs. With an external resistor as a precise reference, we can apply a continuous and negative feedback loop to do either the background calibration or the foreground digital calibration. Even though the background calibration is the most precise over temperature and voltage variation, the dithering noise will degrade the signal integrity. So we may choose the foreground digital calibration as the resistive lag trimming and tolerate the resistance variation over temperature and voltage, which should still be good enough in signal integrity. Thanks for watching. Before you go, if you are benefiting from those key images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with people who may be benefit from it.